Have you ever been stuck waiting for a huge file to download or worried about your private messages being intercepted? We've all been there. Our digital world is built on bits, ones and zeros, sent as pulses of light through fiber optic cables. It's an amazing system, but it's reaching its limits. What if I told you there's a new kind of light, a quantum light, that could change everything? This isn't science fiction. This is the future of how we connect, and it's happening right now. Let's start with the basics. The internet as we know it works by sending trillions of tiny light pulses down glass fibers. Think of it like a massive, super-fast Morse code. A pulse of light is a 1 and no pulse is a 0. This binary system has powered our world for decades, but it has two major weaknesses: speed and security. The more data we cram into these fibers, the more the signals can interfere with each other, causing errors and slowing things down. It's like too many people talking in a crowded room. It gets noisy and hard to understand. And then there's security. When we send data, we encrypt it, but a determined hacker with enough computing power can eventually crack that code. Our current encryption methods are like a strong lock on a door, but given enough time and the right tools, any lock can be picked. As computers get more powerful, especially with the rise of quantum computers, our digital locks are becoming increasingly vulnerable. We are heading towards a crypto apocalypse, where our most secure data, from bank accounts to national secrets, could be exposed. So, how do we solve this? The answer lies in moving from the classical world of bits to the strange and wonderful world of quantum mechanics. Instead of using strong pulses of light, what if we use the smallest possible unit of light, a single photon? This is the core idea behind quantum light communication. In the quantum realm, particles like photons behave in very peculiar ways. One of these behaviors is called superposition. Unlike a classical bit that is either a 1 or a 0, a quantum bit, or qubit, can be a 1, a 0, or both at the same time. Imagine a spinning coin. While it's in the air, it's not heads or tails. It's in a superposition of both states. It only becomes one or the other when it lands, or when we measure it. By encoding information onto single photons in these superposition states, we can transmit data in a completely new way. But how does this make things more secure? This is where another quantum phenomenon, the observer effect, comes in. In the quantum world, the very act of looking at something changes it. If a hacker tries to intercept and measure a photon carrying quantum information, their measurement will disturb the photon's state. It is like trying to secretly read a letter written in invisible ink that disappears the moment you shine a light on it. The sender and receiver can perform a check, and if they find that the photons have been disturbed, they know someone was eavesdropping. They can then discard that key and create a new one. This method, known as quantum key distribution or QKD, allows us to create encryption keys that are, in principle, unhackable. It's not just a better lock, it's a lock that tells you if someone even tried to pick it. This level of security is revolutionary. Financial institutions could conduct transactions with absolute confidence. Governments could secure their most sensitive communications. And you and I could have private conversations knowing with certainty that no one else is listening in. China has already demonstrated this by launching the Mishi satellite, the world's first quantum communication satellite, creating a secure link over thousands of kilometers. Scientists are also building ground-based quantum networks, creating quantum internets, city by city. Now, let's talk about speed. Using single photons might sound slow, but it's all about information density. Because of superposition, a single photon can carry more information than a classical pulse of light. But the real game changer is another bizarre quantum property: entanglement. Albert Einstein famously called it spooky action at a distance. When two photons are entangled, they become linked in a profound way, no matter how far apart they are. What happens to one instantly affects the other. Imagine you have two entangled photons, one in London and one in New York. If you measure the state of the photon in London, you will instantly know the state of the one in New York. This instantaneous connection could be used for something called quantum teleportation. Now hold on. We're not talking about beaming people from one place to another like in Star Trek. We're talking about teleporting information. By using entanglement, we could transfer the quantum state of a particle from one location to another without physically sending the particle itself. This could lead to a quantum internet that is not just more secure, but also potentially much faster and more powerful than anything we have today. It could enable a network of ultra-powerful quantum computers, allowing them to work together to solve problems that are currently impossible, from designing new medicines to creating revolutionary new materials. It would be an internet based not on sending bits, but on sharing quantum states. Of course, building this quantum future is a huge challenge. Single photons are incredibly fragile. A tiny bit of noise or interference from the environment can destroy their delicate quantum state, a problem called decoherence. It's like trying to whisper a secret across a noisy football stadium. Scientists and engineers are working on incredible solutions, like creating ultra-pure diamond crystals and supercooled materials to protect the photons and help them travel further. We need to build photon detectors that are sensitive enough to see a single particle of light and develop quantum repeaters that can extend the range of a quantum signal without destroying it. The road is long and complex, but the progress is breathtaking. What started as thought experiments in the minds of physicists like Einstein and Schrödinger is now being built in labs around the world. We are at the very beginning of a new information age, one that goes beyond bits and into the quantum realm. Just as the classical internet transformed our society in ways we could never have predicted, the quantum internet will unlock possibilities we can't even imagine yet. It will redefine what it means to transmit data, to secure information, and to be connected. So next time you're waiting for that file to download, remember that we're on the cusp of a revolution. A revolution powered by the smallest, most fundamental particles of light. The future isn't just digital, it's quantum. Thanks for watching, and if you're excited about the future of technology, be sure to subscribe for more. See you in the next one.